Hi everyone, welcome. The problem is to design an online judge for system design interviews. It scores system design interviews. Here are some good questions to ask in the requirement clarification phase. Do we need to capture whiteboard drawings or digital diagrams? Do you already have a defined rubric, or should the system design one? How consistent should the scoring be with human raters? What is the latency budget? Do we need explainability? In this slide, we focus on how to convert the high-level online judge for system design interviews into a concrete machine learning formulation. The first step is defining inputs. An interview answer is not a single format object. It may include textual explanations, audio that needs transcription, whiteboard drawings, or even structured diagrams. We also need the interview prompt and rubric because system design answers are tightly tied to context. Additional metadata, such as the candidate's reasoning order or time spent on different components, can provide richer signals for judging depth of analysis. Next, defining the outputs is crucial because the judge must produce more than a raw score. We need both an overall score and category-specific scores, such as API design adequacy, scaling strategy, database choice justification, caching, consistency models, and trade-offs. Additionally, generating explanations helps candidates trust the system and enables transparency. Confidence scores or uncertainty estimates help identify borderline cases requiring human review. For the ML task formulation, this problem is inherently multidimensional. Predicting scores maps naturally to regression. Detecting incorrect or missing components resembles a multi-label classification task. Extracting core system components from freeform text is an NLP task, while evaluating diagrams may involve multimodal vision language modeling. Combining all modalities suggests a hybrid or multimodal approach. When considering model choices, LLM-based evaluators are natural candidates, especially when fine-tuned with expert annotations. However, LLMs benefit from structural support, rule-based modules for checking rubric compliance, diagram interpreters, or modules that verify whether scale estimates are realistic. Some architectures might use an ensemble approach, where separate modules evaluate specific aspects. The objectives and loss functions must enforce both accuracy and consistency. Standard regression losses help with score prediction, while ranking or pairwise losses ensure relative ordering of two candidates remains stable. Preference learning from expert interviewers can refine qualitative judgments. Finally, we must acknowledge challenges, such as inherent human subjectivity in scoring, variability of good designs, and biases across different communication styles. Diagram understanding and multi-step reasoning evaluation remain open research problems. Building robustness and fairness into the model is a core responsibility throughout this ML task framing. Our platform offers easy integration for a smooth setup with your existing systems, while ensuring secure protocols to protect your data at every level, providing peace of mind for your business. This slide covers the foundational data engineering required to build a reliable machine learning-based online judge for system design interviews. The starting point is data collection, which is often the most difficult part because system design interviews are complex, freeform, and multimodal. We need transcripts of real interviews, both strong and weak examples, along with the original prompts and any diagrams candidates draw. These data must be paired with expert scores. Since real data might be limited, synthetic or augmented examples can be generated to ensure model robustness across varied interview scenarios. Next, we move into data cleaning and normalization. Text transcripts may contain filler words, transcription errors, or ambiguous phrasing. These must be cleaned and standardized. Diagrams might come in many formats: PNG screenshots, PDF exports, or whiteboard photos. Converting diagrams into structured JSON-like representations, identifying nodes, components, and data flows, allows models to use them effectively. It is also crucial to normalize scoring labels across multiple annotators because experts naturally vary in strictness. The labeling and annotation pipeline is critical because the ML judge learns from human scoring patterns. We need multi-dimensional labels: overall score, API quality, scaling plan correctness, storage design sophistication, trade-off depth, and more. Multi-rater labeling helps create a more stable ground truth. Developing clear annotation guidelines is necessary to reduce variance and ensure reproducibility. Feature engineering is where raw data becomes learning ready. For text, features include extracted architectural components, consistency across requirements, and reasoning flow. For diagrams, features include node types, edge counts, bottlenecks, and presence of industry-standard components, e.g., load balancers, caches. Metadata, such as time spent on different parts of the solution, also becomes a signal of reasoning depth. Finally, data quality and governance ensure the model is fair, reliable, and maintainable over time. We must track data versioning, maintain documentation, and monitor biases, such as bias against candidates with certain accents or communication styles. Drift detection helps ensure the model remains aligned with evolving interview formats. This holistic data engineering foundation enables the model to evaluate candidates accurately, consistently, and fairly. Our case study highlights a 50% increase in productivity by implementing our platform to streamline workflows, achieving double the project delivery speed, and delivering results within just 3 months. Let's break down the ML model architecture for our online judge system. 1. Input layer. The input layer takes all relevant information from a submission. This includes the raw user-submitted code, problem descriptions, programming language, and metadata such as difficulty, historical user performance, and prior submission outcomes. A well-designed input layer ensures the model captures all context needed for accurate predictions. 2. Pre-processing and embedding layer. Before feeding the data into the core model, code and text are pre-processed. This includes tokenizing the code into meaningful tokens, keywords, operators, identifiers, and converting problem statements into embeddings. Language-specific features such as syntax trees, API usage, or code length are also encoded. Pre-trained embeddings, like CodeBERT, or custom embeddings, can be used to represent both code and text semantically. 3. Core model/encoder. The encoder is the central part of the architecture. Transformer-based encoders are commonly used for capturing long-range dependencies in code and textual descriptions. Alternatively, LSTM or graph-based models can encode structural information from code ASTS or control flow graphs. This layer outputs rich contextual embeddings that represent the semantic meaning of the code in relation to the problem. 4. Task-specific layers. On top of the encoder, task-specific layers predict the outputs needed. For example, a classification head predicts whether a submission passes all test cases, while a regression head estimates runtime or memory usage. Multitask architectures can output multiple metrics simultaneously, such as error type classification, efficiency ranking, and correctness prediction. 5. Output layer. The output layer provides the final predictions, which can be a probability of correctness, expected runtime, or feedback suggestions. These predictions can guide automated grading and personalized user feedback. 6. Regularization and optimization. Regularization techniques such as dropout and layer normalization help prevent overfitting. Appropriate loss functions like cross-entropy for classification or mean-squared error for regression are used to train the model efficiently. This architecture provides an end-to-end ML solution for predicting submission outcomes, helping the online judge system become adaptive, intelligent, and scalable. Let's discuss how we evaluate the ML model for the online judge system, both offline and online. 1. Offline evaluation, accuracy/F. 1 score. Offline evaluation involves testing the model on historical submission data that the model has not seen during training. For classification tasks, such as predicting whether a submission passes all test cases. Metrics like accuracy, precision, recall, and F1 score are used. These metrics help us understand how well the model can correctly identify passing versus failing submissions. 2. Offline evaluation, regression metrics. For tasks predicting runtime, memory usage, or efficiency scores, we use regression metrics such as mean squared error, MSE, and mean absolute error, MAE. These metrics quantify the deviation between the predicted performance and the actual execution metrics, helping us understand the model's precision in continuous outputs. Third, offline evaluation, multitask metrics. In a multitask setup, the model may also predict error types, partial correctness, or ranking of submissions. Task-specific metrics such as weighted F1 score or ranking correlation coefficients, like Spearman's RHO, are used to measure performance for these additional outputs. Multitask evaluation ensures that the model performs well across all relevant dimensions. 4. Online evaluation, A/B testing. Offline metrics cannot always capture real-world performance. A/B testing involves deploying the new model alongside the current production system for live submissions. By comparing metrics such as prediction accuracy, speed, and system load, we can measure the practical effectiveness of the model before fully replacing the baseline. 5. Online evaluation, user impact metrics. Ultimately, the model's value is measured by user impact. Metrics include increased submission success rates, reduced manual review effort for interviewers, improved user satisfaction, and better quality of feedback. These indicators show how the ML system improves the overall online judge experience. 6. Monitoring and continuous evaluation. Even after deployment, the model must be continuously monitored. Submission patterns may change over time, causing model drift. Monitoring metrics, error distributions, and user feedback triggers retraining or adjustment to maintain long-term reliability. This combination of offline and online evaluation ensures the model is accurate, robust, and beneficial in practice. Let's go through how the ML model for the online judge system is deployed and served. 1. Containerization and packaging. Before deployment, the model is packaged with all its dependencies using containerization tools like Docker or MLflow. This ensures that the model behaves consistently across different environments, from local development to production servers. Packaging also allows version control of the model, making it easier to reproduce past results or roll back to a previous version if needed. Second, serving infrastructure. The deployed model is exposed via REST or gRPC APIs as a microservice. This architecture allows the online judge system to send new submissions to the model and receive predictions in real time. Microservices make it easier to scale individual components independently, and APIs provide a clean interface for integration with the front-end system. Third, scalability and load balancing. Online judge systems often experience bursts of submissions, particularly during interviews or coding competitions. Horizontal scaling ensures that multiple instances of the model service can run in parallel. Load balancers distribute requests across instances to avoid bottlenecks and maintain low latency. Auto-scaling policies can dynamically add or remove instances based on traffic. Fourth, caching and latency. Optimization. To improve response times, frequently requested predictions can be cached. For example, repeated submissions of the same code can return cached predictions. Asynchronous processing can also help, allowing the system to return preliminary results while performing more detailed analysis in the background. 5. Monitoring and logging. Monitoring is critical to detect failures, track latency, and ensure accuracy. Metrics such as prediction response time, error rates, system load, and model drift are logged continuously. This helps the engineering team maintain service reliability and identify when the model needs retraining. 6. Continuous deployment and rollback, CI/CD pipelines, automate model deployment, testing, and versioning. This ensures new model versions can be released safely. Rollback mechanisms allow reverting to previous stable versions if issues are detected post-deployment. With this architecture, the ML model for the online judge system can serve predictions efficiently, reliably, and at scale, providing a smooth experience for both candidates and interviewers.